I needed to make a precision timer for some stuff I'm doing, so I thought I'd make one out of discrete electronics. Although I could have used a microcontroller, I thought discrete electronics might be a bit better because they do exactly what they're supposed to do, whereas a microcontroller you have to take into account interrupts and the timing of the microcontroller and things in software. Although I might have a go at doing it in a microcontroller a bit later as well, because there are certain things that discrete electronics are a bit difficult to do as well. So if I show you the back of this circuit, there's a lot of wiring because each of the pins has to be wired up to something. But in this video what I'll do is I'll take you through the actual testing of the device, making sure it's accurate and it works, and then I'll go through the design of the device and how it all goes together and how it works. So to test the device, I've put together another little circuit, and this is just a crystal oscillator. So on here I've got an 8 megahertz crystal and a driving circuit, which is over here, and then I've got a counter circuit which divides the crystal down into various stages. So I've got a series of pins on this side, and the top pin is the 8 megahertz coming straight out, and then it's divided by 2, divided by 4, divided by 8, 16, 32, 64, 128, and even 256. That way I can get different measurements out so that I can test on the actual timer circuit itself. This just runs off of a PP3 battery, and it connects into the side here where I've got all the connections going into precision timer. So on the side I've got a reset switch to reset the precision timer, because it will take one time in and then it will stop timing, so I can reset it and take another time in. And on the front I've got a 5-volt supply to power the actual precision timer. So first of all I'll power up the precision timer. I've got a boost converter here. It's just going to, I'm powering it directly by 5 volts. And I haven't got it automatically resetting this circuit, so if I hit the reset button it resets. It's not timing anything at the minute because I haven't connected the battery here. So if I connect that'll get the oscillator running. And the first thing I'm going to time is off of the direct 8 megahertz. So the 8 megahertz should provide a certain figure. So for an 8 megahertz clock cycle, the value I'd expect to see on the timer would be 1 over 8,000,000, so that's the inverse of 8 megahertz. And so this is what I expect to see, but I've only got 8 7-segment displays, so I only expect to see 1, 2, 3, 4, 5, 6, 7, 8. I only expect to see the last value on the 7-segment display to be a 1, but because there's an extra 0.25 above that, it could be a 2 or a 1 because of potential error. When I reset the circuit, I get 2 out. So it should have provided 0.000001, which is 100, where it should be 125 nanoseconds. So I'd only see the 100 nanoseconds appear here. Because it's showing 0.2, that's showing that the error on this is going to be 100 nanoseconds plus. So if I reset it again, I get the same figure. And that's a really good figure to get out first of all as the 8 megahertz one, because that shows that it will count down to even the least significant figure. So its precision is guaranteed to be 100 nanoseconds plus possibly another 100 nanoseconds depending on what stage it starts counting. So next I'll move the divider onto dividing by 2. So now I should be operating off of, so it was 8 megahertz going straight through, now it's 4 megahertz. So now for a 4 megahertz clock cycle, because I'm dividing by 2, so 1 over 4,000,000, and I expect to see the 8 digits, 1, 2, 3, 4, 5, 6, 7, 8. So this time I expect to see a 2 on the display, and it's possibly plus another 1, so it's 2 or 3 I expect to see on display. And I should be getting a value of about 0.2 here, but 0.25 So it's probably not going to make much difference. But if I reset the timer, so 0.2 still, I'll do it again. 0.3. So it's showing that it's still got the 100 nanosecond error rate, but that's showing that it's actually counting higher. So this should be 0.2 and then 5 afterwards. So that's looking good at the minute. So next I'll divide by 4. So dividing by 4 gives a 2 megahertz clock rate. So the inverse of 2,000 gives this, which is 1, 2, 3, 4, 5, 6, 7, 8. So it should just have a 5 on the last digit. And now I should get a 5 on this very last digit here. So, and that's an exact figure, so there's no remainder afterwards. That should be exactly 5. So I reset, and I'm getting a 5. I'll do it again. 5. So that's another really good sign. Okay, so now I'll jump straight to the last clock output, which is divided by 256. So now I'm dividing by 256. So if I take the 8 megahertz and divide by 256, it gives me 31 kilohertz, which I'm going to be measuring. So if I invert that to 1 over that, that gives me an output of 1, 2, 3, 4, 5, 6, 7. So there'll be an extra digit on the end. So I should get 320 on the end of the display. So now what I should be getting on here is 320. So this is the real test. It will show if it's actually accurately counting a higher sum rather than just like going for these really small figures. So I'll hit reset and 3, 2, 1. So that's 100 nanoseconds out. I'll try again. Yeah, so it's 100 nanoseconds out, but it's showing it's actually counting extremely precisely, and that's exactly what I want for doing some more experiments. So now what I'll do is I'll disconnect the test circuit and the power as well, and I'll go through the design of the actual circuit itself. Okay, so I've got a circuit diagram of my actual design. So I did this on KiCad first, although I didn't make a PCB on KiCad. Maybe I should have, because maybe it wouldn't have been this rat's nest, but I decided to take the strip board approach to actual design for this particular one, for just like as a prototype. And I'll start from the output, which is the 7-segment displays, and work myself backwards at first. So starting from an 7-segment display, all of the 7-segment display circuits are exactly the same. So you've got 7-segment display here. It goes through a 74393, which is a 4-bit binary counter, which is over there, and it goes to a 7447, which is a 7-segment display driver. So the 7-segment display driver has limiting resistors for each of the segments and goes to the directly to the 7-segment display, but the counter itself goes into the 7-segment display driver just as a binary number, but the 7447 takes binary coded decimal to represent the values 0 to 9, although the counter will actually count past 9. It will count all the way up from 0 to 15. So in order to make it roll over when it gets to 9 back to 0, I'm using an AND gate here, and I'm taking it off of the counter line, so that this one has a value of 2, 4, 8, and 1, 2, 4, and 8. So I'm taking from 4, which is 2, and 8, which add together to make 10. So when the count gets to 10, it goes through the AND gate, and it goes through an OR gate, and I'll come back to the other input of the OR gate, but one of the inputs of the OR gates is this when it gets to 10, and it goes into the reset of the counter. So the counter will just count from 0 to 9 and then back to 0 again, 0 to 9 back to 0. But there's another thing which happens on that reset. So it goes up this line here, and it goes into the input of the next counter. So as well as resetting back to 0, it'll add one to the next counter. So that's how it ripples through all of the displays. So like I say, identical circuits for all the displays start off with a count going to then each one ripples from 9 to 0 and adds one to the next display. And it's literally the 7-segment display circuits is literally just a counter circuit which counts all the way up across all the displays from here to that, one to the next one to the next one, all the way to the end. And like I say, I'll come back to the other input of the OR gate, which resets the displays a bit later. But what it literally does is it's there to it's part of the reset button. So the reset button gets to it through a different separate bit of circuit, which I'll cover, and it goes to all of the displays. So the reset button can just reset the count to 0, and it can start the timing again from there. But that description covers all of this top part of the circuit, which is the 7-segment display drivers. And now it's just the bottom part of the circuit which I need to describe. So I'll start describing the bottom part of the circuit from the opposite end, from the actual source of the count, which is over here. So I've got a crystal resonator, and this is actually a 20 megahertz crystal. So I'm counting pretty much the limit of what TTL circuits can count at. So, I think they can go up to about 35 megahertz, and this actually drives it at 20 megahertz. And that's all that this does. Is there's a couple of Schmidt inverter circuits which are actually used to drive the crystal. So the crystal produces a very small signal, a very low level signal, but you need these inverter circuits to be CMOS, because CMOS can use very small amounts of current. So what they'll do is they'll amplify the current into a very big current. And they're also Schmidt triggers. So Schmidt triggers have this thing called hysteresis, and when the signal's rising, it will take a short period to get to the point where it actually recognizes a 1, and then it take a very long period to drop back down to 0 again. But when it starts to drop back down to 0, it will drop back down very rapidly, and then it will again do the same. In that when it goes back to 1, it will go very slowly at first and then very suddenly, and that reduces noise and it increases the accuracy of the actual crystal driver. So if you're going to build one of these crystal circuits, you definitely need CMOS version of a Schmidt inverter circuit. That goes into a 74393, which is a 4-bit counter like I had on the displays, but that 4-bit counter, it just does divides the clock input from 20 megahertz to 10 megahertz, and that's done for a reason, because when I'm actually counting out displays, what I'm doing is putting the count of the 10 megahertz directly on this display. So we got 0, 0, 0, 0, 0, 0, 1, 1, 0. So that's 10 megahertz again. So every time that this display becomes a 1, that's 10 megahertz being counted. So that's a 1-second display then. So I've hard-coded or hardwired this decimal point to be on all the time, because that'd be seconds, so it count up to 9 seconds, 999, 999, 9. And then that decimal point is fixed, because this is a dedicated circuit which only counts in hundreds of nanoseconds. Yeah, so just to sort of describe that, so seconds, tenths of seconds, hundreds of seconds, milliseconds, the next 3 digits are microseconds, then nanoseconds. So you just got the 100 nanoseconds on the very end. That's the precision of the circuit. So it comes out of, so this divides by 2, so we've got 10 megahertz coming out of there, and it goes into an AND gate. Now the AND gate is there so that I can start and stop the count going. So the output of that goes straight into the first digit of the counters, but I don't want it to be counting all the time. I want to be able to control when I start and stop it. I don't want to start and stop the actual oscillator itself, because oscillators take a while to get up and going, so you'd get erroneous counts if you were trying to stop and start an actual oscillation. So the oscillation happens all the time, but what I can start and stop here is the 10 megahertz count. So there's 2 inputs to that AND gate, and the other input comes from something which I can actually control switching on and off, and it's the other 393. So there's, in 74393, there's 2 counters, and so in one of the circuits, this is the other counter to that one. But this counter, so that one does the divide by 2, but this one doesn't. This one, it's like a sequencer. So the first count it gets enables the count to go through to so it starts the count on the 7-segment displays, and then when it counts up again, it stops the count because it's counting from 1 to 2. So that will stop the count. But also, when it stops the count, this wire that comes out of the 2 goes back and inhibits any more signals coming through to say start counting again. So until there's a reset signal, this will just stay stuck in saying don't tell me to do anything more until I get a reset, in which case when you reset, it goes down to 0 and waits for the first signal again to start counting. And then there's only really 2 other bits of the circuit, and they're in a single chip, but there's 2 of them. There's they're monostable multivibrators. So what they do is when they get a signal, they give out a pulse, a single pulse. And so one of them is the reset signal. So and that's this one over here. So the reset button comes in from over here and triggers that monostable multivibrator. And yeah, it's got quite a high value on it, 10 microfarads. So that when on this last digit over here, the decimal place here, you could see when I was hitting the reset button, that lights up for the period that the reset happens, and then when it goes out, that's the end of the reset. So this one just creates, so when you press the reset button, it creates a big enough pulse that you don't, because you don't want the press of the switch, which can have like noise on it. You don't want that to just keep turning on and off and doing funny things to the circuit over here. So I've created a long pulse here that when you press the reset button, you've released it and it's still holding in reset for a period of time after you've released the reset button to make sure there's no noise which can disturb the rest of the circuit, so you get a very precise count. And then the other monostable multivibrator, that just counts the sequencer. So this sequencer where it says it starts and stops a count, or it inhibits anything extra from happening, which comes back here and tells the multivibrator it puts it into a state where it won't re-trigger. So this one comes from wherever you want to time, which in the case of the test circuit that I was just doing, it comes from the output of the clock, and the first rising edge will trigger it to start the count, and the next rising edge, which will be after a full cycle, will trigger it to stop the count and inhibit stuff. So actually it's a very simple circuit. When you lay these discrete circuits out like this, they look a lot more complex than they really are in theory. There's a lot of wiring to go on. I definitely want to try doing this in microcontroller as well. That'll have certain advantages in that it'll take very little electronics, it's all programming, but the disadvantages are you've got things which happen in microcontrollers, which like instruction cycle times, interrupts occurring, and the fact that you are already dividing a counter down to be the instruction cycle, so the instructions are quite large in sort of comparison to the amount of time you're trying to actually time. So it'd be interesting to see how that would compare. I wanted to make this discrete circuit because I know it's going to be very accurate. As long as it works, then it'll work precisely, and that's exactly what I found with this circuit. So I can actually use this to do some precision timing.